Hello students. Welcome back to class. I hope you're all prepared for today's lesson as we explore the topic of properties of waves. Before we move forward, let's take a moment to review what we covered in our previous class. In our previous class, we explored the topic of conversion of energy. How energy can be transformed from one form to another. And also devices used in energy conversion, including generator, car battery, drums and cymbals, electric iron, and others. In today's class, we will focus on the interference of waves in light and sound, the diffraction of waves in light and sound, and the polarization of light and its application in Polaroid. Alright, let's refresh our minds on waves. A wave is simply a disturbance that moves through a medium, carrying energy from one place to another. But what exactly do we mean by a medium? A medium is any substance or material that a wave travels through. It could be a solid, a liquid, or a gas. Think of it this way: imagine you drop a pebble into a pond. You see ripples spreading out. The water in the pond is the medium it carries the wave as it moves outward. A quick review of our understanding of a wave graph, which consists of key components such as the crest, the highest point of a wave; the trough, the lowest point; the wavelength, the distance between consecutive crests or troughs; and the amplitude, the maximum displacement from the rest position. Let's talk about interference of light waves. This happens when two or more light waves overlap and combine to form a new wave pattern. They are applicable to both light and sound waves, but they behave differently due to their nature. We have two types of interference: constructive and destructive interference. Constructive interference. Imagine two waves moving toward each other. When their crests, highest points, and troughs, lowest points, align perfectly, they combine to form a larger wave with greater amplitude. The individual wave amplitudes add together, resulting in a stronger overall effect. On the other hand, destructive interference. Now, what if a crest from one wave meets a trough from another? Instead of getting bigger, they cancel each other out. The result is a much smaller wave or even complete silence in the case of sound waves. I know this might be tricky, but stick with me as we dive into the practical experiment. Let's connect the dots between these ideas with this experiment. The double-slit experiment is a demonstration of light's wave-like behavior, relying on coherence, where waves maintain a constant phase relationship over time to produce stable interference patterns. Let's break it down step by step. Step 1. Let's start with a laser, which produces a very special kind of light. Unlike normal light from a bulb, laser light has waves that are perfectly aligned in phase. This means the peaks and valleys of the waves match up as they move forward. This is what we call coherent light because the waves don't randomly change phase. Step 2. The barrier with two slits. The laser light shines on a barrier with two tiny slits. When the light reaches the slits, something interesting happens: it spreads out. These spreading light waves from both slits act as two new coherent sources of light. Step 3, which is the last step. Interference on the screen. The two sets of light waves travel forward and meet on a screen. Sometimes, the waves from the two slits arrive in sync, with their peaks and valleys matching perfectly, creating bright bands on the screen. This is called constructive interference. Other times, the waves arrive out of sync, with one wave's peak matching another's valley, cancelling each other out and creating dark bands. This is called destructive interference. The result is a pattern of bright and dark stripes called an interference pattern. Let's look at some examples. When sunlight hits a soap bubble, some of the light bounces off the outer surface, while some passes through and reflects off the inner surface. These reflections blend to create bright rainbow colors. Similarly, when rays of sunlight hit a thin layer of oil on the surface of water, some reflect off the surface of the oil while others reflect off the water surface. These reflections combine together to create the bright rainbow colors we see. Likewise, the tiny grooves on CDs and DVDs scatter light in various directions, creating vibrant rainbow patterns. Congratulations on completing this lesson. You should be proud of yourself. Answer the following questions. Don't be discouraged if you don't get it right the first time. Remember that getting it wrong isn't a failure, it's an opportunity to understand the topic better. In summary, we have covered so far on the interference of waves in light. In our next class, we will move on to our next objective, interference of waves in sound. I hope today's lesson provided you with valuable insights. See you next time. Thank you.